Okay, I believe we are live and I can see the number of attendees is rising up. So let's begin with a welcome, everybody, to this, the second in a series of webinars from Veramaris. What can you expect in return for spending your time with us here today? Well, our main purpose is to support the transition to Optimum Omega Nutrition as the industry continues to get to grip with new innovations like our algal oil and seeks to restore the levels of essential fatty acids in aquaculture feed. We're going to explain how algal oil contributes to the health and welfare through supporting the physiological responses in Atlantic salmon. And why is that important? Because health remains the greatest challenge for aquaculture, impacting not only the productivity of aquaculture businesses in the sector, but also very importantly, impacting the welfare of the animals that are being held on fish farms all around the world. I'm Ian Carr, I'm responsible for business development in Veramaris, and I'm very happy to be able to connect with you all again today and focus this time on salmon farming in Norway. But if salmon farming isn't your thing, stay tuned because there are transferable learnings from this webinar in the broader sense too. And that's because essential fatty acids like EPA, DHA and ARA are of course indispensable for the health and welfare of shrimp and marine fish too. In terms of process, the webinar today lasts for an hour overall and the session runs in English. First of all, we're going to enjoy a very detailed, insightful presentation from Professor Brett Glencross, who I'll introduce in a moment. And then we're going to continue with our panel today, which includes Kåre Gruven from Norway Royal Salmon, independent consultant Dr. Neil Ochterlony, and Ragnhild Bleckenrud, who is the Veramaris lead for Norway. So we'll meet Kåre, Neil and Ragnhild a little later on. You can also take part in the discussion today by registering your questions in the panel on the right-hand side of the screen. You register them as questions under the chat function, and we'll get to some of those in the panel discussion later on as well. But let's first of all start by learning more about why omega nutrition matters. And Brett, I'd like to ask you to turn your webcam on. Take pleasure in introducing Professor Brett Glencross. He is Professor of Nutrition at the Institute of Aquaculture and the University of Stirling here in Scotland. Brett's worked a lot in academic, institutional and industrial roles all over the world. Is very well known to fish farmers, feed producers, different stakeholders throughout the value chain. So therefore, we welcome you, Brett, and we look forward to receiving your talk.
Thanks, Ian. Afternoon, everybody. Thanks for that introduction, Ian. What I was going to talk to you about today was the physiological responses that we see in farm salmon to Optimum Omega Nutrition. But before we launch into that, I thought I'd quickly go over some of my background because it sort of flavors my perspectives in some respects. I started my journey in working on essential fatty acids about 25 years ago with my PhD, where I did a lot of work on prawns, understanding all the requirements for all 5 essential fatty acids in Penaeus monodon. About 10 years after that, I circled back around into the fatty acid world by starting work on Asian sea bass, barramundi, and looking at defining the requirements there for DHA, EPA and ARA in that species. And then about just under 10 years ago, I started working on salmon. And then 5 years ago, I moved to Scotland from Australia. And most of my work here in Scotland, the Institute of Aquaculture at the University of Stirling, has actually been on various aspects of omega-3 requirements in salmon and the physiology there. So I sort of had a long background coming at it from a range of different perspectives, whether it's invertebrate versus vertebrate, tropical versus temperate. And that, in some respects, I think gives me some new perspective on the way in which we look at the requirements for these nutrients, which is a little bit different from the way that many others look at it. So let's look at what biologically defines essentiality for these nutrients. Now, all organisms can make fatty acids to a certain extent. That fatty acid at the top there, 18,1, N-9, omega-9, can basically be made by all organisms. Virtually everything on the planet has the ability to make that. However, converting that 18.1 omega-9 into 18.2 omega-6 or 18.3 omega-3 is something that really only plants can do. Once those omega-3s, the 18.3 omega-3 or the 18.2 omega-6 are made though, a range of animals can actually metabolize those nutrients further. And they use these pathways we see here in front of us and a whole suite of different enzymatic machinery to facilitate that conversion of those short chain polyunsaturates, the 18.3 omega-3 and the 18.2 omega-6, into the longer chain, more highly unsaturated versions like EPA, DHA, and ARA, which are so biologically valuable. However, that process of that conversion through all those enzymes, generally there's one enzyme which seems to regulate whether it goes the full way through to DHA or not, and that's that delta-5 FADS1 enzyme. And this sort of really defines the need whether an animal can get away just having the short-chain polyunsaturates in its diet, or whether it needs the long-chain polyunsaturates preformed in the diet. And if the activity of that enzyme isn't great, whether there's actually advantages to being provided with that long-chain polyunsaturates in the diet in the first place. However, the other aspect that we see among animals, this is data from Atlantic salmon, is that enzymatic machinery varies amongst different tissues. So the three key enzymes we look at when we're looking at this synthetic process of converting the short chain to the long chain are those enzymes of the 5-FAD, the 6-FAD, and the ELOVL5. And the expression of these enzymes varies amongst tissues. You can see here, looking at this red and green map on the side, that we see the brain and liver generally being the most active and the head kidney being the least active. And this, we believe, reflects the metabolic capacity of these various tissues to actually undertake these elongation and desaturation reactions, which is sort of probably linked to their demand within those tissues or their ability to actually undertake that synthetic capacity. When we look at Atlantic salmon, the Atlantic salmon is one of those species that can actually take the short chain fatty acids and convert them into the long chain fatty acids. Now, this was a recent study done in the group here I work with Doug Tocker and Monica Betancourt, and we ran an experiment a couple of years ago where we looked at 4 treatments. One treatment that had preformed supplies of EPA and DHA, and the other 3 diets, A, B, and C, had no long-chain polyunsaturates at all in the diet. They had varying ratios of the 18.3 omega-3 and the 18.2 omega-6 at a ratio of 3:1, 1:1, or 1:3. And then we fed these diets to salmon from first feeding. So these animals had never seen long-chain polyunsaturates prior to this point in their life. Now, the first thing to notice from that is that the fish that were fed the preformed long-chain polyunsaturates clearly performed better than those that were just supplied with the short-chain polyunsaturates. Those animals that were fed the short-chain polyunsaturates, they grew okay. They just didn't grow anywhere near as much as the other ones, less than half, in fact. But survival was fine. What we did also note is that the animals did take those short-chain polyunsaturates and biotransform them into the long-chain omega-3 and long-chain omega-6. However, how much of that synthetic activity occurred was influenced by the abundance of the 18.3 omega-3 or the 18.2 omega-6 that was in the diet. What you can see in the middle graph there on the bottom is that when we had high levels of the 18.3 omega-3, we certainly got the best levels of endogenous production of these longer chain polyunsaturates, the 25 omega-3, 22.5 omega-3, and 22.6 omega-3, DHA, when there was a high level of that 18.3 omega-3 in the diet. As we decreased the omega-3, 18.3 omega-3 in the diet, the total productivity of that long chain polyunsaturates reduced. And as we increased the level of the 18.2 omega-6 in the diet, the production of the long chain omega-6s like arachidonic acid began to increase. What was really interesting though is to notice as we look at the far right graph in this presentation, and that, in fact, that middle data there, that DHA to EPA ratio, what we saw is that as we changed that ratio of the level of linolenic, the 18.3 omega-3 to linoleic, 18.2 omega-6 in the diet, is we also influenced that ratio of DHA to EPA. But generally it was pretty tightly conserved around about that ratio of 3:1 to 5:1 of DHA to EPA in the animal's body. So in some respects, what the salmon was telling us is that it wants, irrespective of what their substrate is at the beginning, it's trying to conserve a ratio of EPA, DHA to EPA in its body. Now that's the quantitative analysis of what the animal's doing in terms of its utilization of the short-chain polyunsaturates and its synthesis of the long-chain polyunsaturates. But when we look at some of the quantitative requirements, this is some of the work that was done about 25 years ago by Bente Reuter and Afima as part of her PhD studies. This is what we arguably look at as the original omega-3 salmon work, where we first explored the quantitative requirements in the early stages and in fingerling stages. Now, what you can see on the left-hand figure is that when we provided EPA and DHA together in the diet, we got an improvement in performance, growth performance, up to about an inclusion level of 1% of the diet. And then after that, it sort of plateaued or came down only slightly. We also got an improvement in performance through the inclusion of the 18-3 omega-3, the linolenic acid. But the animal didn't really respond to the presence of the 18-2 omega-6. So it's clearly telling us that it really wants these omega-3s, but it would rather have them as the EPA and DHA in the diet. What's the other important observation from this study was that the growth optimal level was at 1% of the dry diet, but in terms of the survival, this is obviously the mortality data here, so obviously the lower the number, the better, is that the best survival was actually at a level twice that of the optimal for growth. So we can clearly see that the growth and mortality benefits don't necessarily occur at the same inclusion level. When we transition salmon from freshwater to a saltwater environment, they go through quite a physiologically challenging process we refer to as smoltification. And we can see that diet can have quite an important influence here. This is some work from around about 20 years ago, where Doug Tocker and colleagues looked at measuring the fatty acids in the phospholipids of the liver during that transition from freshwater to saltwater. And what we can sort of see is as the animal comes into that smoltification period, it elevates the levels of arachidonic acid and DHA in its liver, and EPA is maintained low. After it transfers to saltwater, though, the levels of arachidonic acid stay initially high and then they come down, whereas DHA comes down straight away, but EPA, interestingly, escalates. It increases after the transfer to saltwater period. So we can sort of see here that there's quite different requirements for what we're seeing in the animal's body pre-transfer and post-transfer. Pre-transfer, it's clearly wanting DHA and ARA, but post-transfer, it appears that EPA is the main fatty acid that it really needs for that post-seawater phase. Continuing on with some of the quantitative studies in terms of the requirements for long-chain omega-3 by Atlantic salmon. This was a series of 2 studies, both done by independent groups around about 5 years ago. And what was good about both these studies is they both sort of corroborated each other and showing that the estimate for quantitative requirements was about the same level. What it identified is that the level of DHA required was around about 10 to 15 grams per kilogram of the diet. But also, if we looked at the inclusion of those omega-3 in the diet as just EPA or EPA plus DHA, it didn't seem to change that estimate of that requirement. It still stayed at around about 10 to 15 grams per kilogram of the diet. So it sort of appears that the animal, in terms of growth at least, is a little bit ambivalent as to what that omega-3 comes in, whether it's DHA or whether it's EPA. It seems to be quite sort of adept at making use of both nutrients to sustain its growth performance. Other studies that were done around about the same time, this is the study that came out of Greta Rosaland and the group at IMR in Norway. They took a similar approach, but looking at also that study over a much longer period of time, the full production cycle, and also looking at different temperatures, 6 degrees or 12 degrees. They also looked at presenting their data in a different format in terms of presenting it in terms of the percent of fatty acids. And this raises another question as to, well, what is the right way to look at it, fatty acid requirements? Are they a function of the diet, or are they actually a function of the total abundance of fatty acids? And we'll answer that question in a minute. But what this study here showed was that where this data plateaus at the bottom, in this case we're measuring at retention, so we can see the decline to the point where there's no more change in retention efficiency. It's sort of identifying that as the optimum level for the omega-3 in the diet. In this case, it occurs around about 3.4 to 5.2% of total fatty acids, which ironically is around about that 11 to 15 grams per kilogram of the diet again. So it appears that irrespective of whether we do the trial for the full production cycle or whether we do it for only as short as 9 to 12 weeks, we can sort of end up with the same answer to a certain extent. But we also saw that that retention was unaffected by whether the temperature was 6 degrees or 12 degrees. So within normal physiological regimes, it doesn't appear that the temperature makes a big impact in terms of the optimal requirements for the species either. Going back to that question that was raised in the previous slide, and that question is, are omega-3s needed as a proportion of the diet, or are they needed as a proportion of the lipid? Now, this was a bit of recent work that only sort of was published last year, or came out this year, in fact, where we looked at a study of 4 different diets. Each of those diets had basically either 1 or 2 different levels of omega-3, 7 or 15 grams per kilogram, or 1 or 2 different levels of lipid, 18% lipid or 23% lipid. And the diets were balanced to make the mice energetic, so there was no energetic differences occurring in this study, because we know energy intake can have a really marked impact on performance of salmon. Now, what we found when we ran that experiment is that in the diets with the high level of lipid, what we saw was a clear difference or clear impact of the level of omega-3 on performance. But when we decreased the level of lipid in the diet and then compared the levels of omega-3, we didn't see any difference in the effects. Now, well, the way we interpret this is what it shows is that at high lipid levels, those same absolute levels of omega-3, 7 and 15, obviously basically become a little bit lower, and therefore they become sub-threshold. Whereas the other diets with the lower level of lipid, those same absolute levels of omega-3 are slightly at threshold or super threshold. So the way we might interpret that is in the graph on the right, where if you look at this response, this nutrient-dependent plane to energy-dependent plane break at 5% of total fatty acids, you can see where the red diets would line up and where the blue diets would line up. So what's the implications of that? Well, if we look at, let's say for an example, in this study here where those 2 different diets, for example, we can see them overlaid from the previous experiment on this graph here. On this graph here on the bottom, we have the total lipid content of the diet. On the left-hand side, we have the total abundance of the long-chain omega-3 in the diet in grams per kilogram. And on the right-hand axis, we have the proportional, or the relative amount of total fatty acids as a percent of the total fatty acid abundance. Now, if I take an example of that, say for example, 200 grams per kilogram of lipid in the diet, and look at, say, 5% of the total fatty acids being present as omega-3, that means the total absolute amount of omega-3 I need is around about 10 grams per kilogram in the diet. If I was to increase the lipid in my diet, though, to say 300 grams per kilogram, and I'm still looking at that critical threshold there of 5% of total fatty acids, I now need 15 grams per kilogram of total omega-3 in the diet to be at that same level of 5% threshold. If I'm to increase my level of lipid again up to 400 grams per kilogram, now you can see that if I'm staying at that same threshold point of 5% of my total fatty acids as omega-3, I'm now needing 20 grams per kilogram of long-chain omega-3 in the diet. So what it's showing is that as we change our level of lipid in the diet, we so too need to change our total abundance of the omega-3 in the diet simply to stay level with that proportionality rule that we've identified as being the nature of requirements for fatty acids. So what does this mean in terms of the production requirements and how this is being actually applied out in the real world? Well, we can see below a level of around about, say, 1% of the diet, or below 3 or 4% of the total fatty acids in the diet, we see signs of deficiency symptoms in Atlantic salmon. Above this threshold, somewhere between 1% to 2% of the diet, or 3 to about 5.5%, what we see is under ideal conditions, this is the threshold point of what the animal actually needs. However, most commercial feed companies take a degree of conservatism, and so they start putting their inclusion levels in the feeds a bit above this range, from about 1.5 to 2.5, somewhere around about 4% to 7% of total fatty acids. And what we see is actually some leading scientists and leading farming groups now, actually, they're even going beyond that, because what they're recognizing is that there's other benefits beyond growth that we're seeing with omega-3. And that's sort of where I'm going to go with the rest of this presentation, to talk about what some of those other benefits are beyond the growth responses we can measure. One of the key ones that we've seen recently is that we can see that with these higher levels of EPA and DHA in the feed, is that it improves fish quality. There's evidence now that we can see that there's improvements in pigmentation, principally through measurements of salmonfan score, that with higher levels of EPA and DHA, we can see an improvement level of that salmonfan score. And this, of course, results in basically a reduction in the level of downgrades to low pigmentation. The other quality effect that we've seen is there's been a reduction in the melanin spots in the fillet. We can see as we increase the level of EPA and DHA in the diet above that threshold at 1%, and then go up as much high as 3.5% of the diet, we get a progressive increase in the quality of the fillet by a reduction in the number of melanin spots. And of course, this is again resulting in a reduction of the number of downgrades in the flesh quality through both that improvement in the number of melanin spots and also the improvement in the color fan score. However, where perhaps the omega-3 seem to have their strongest impact and the strongest benefit above and beyond that level we see with growth is actually their ability to support animals in stressful conditions. Now, this was some data that was published around about 4 years ago by Marta Bauer from the group at NOFEMA, where they looked at 3 levels of EPA and DHA in the feed, and the animals were farmed in sea cage conditions that were quite challenging. There was obviously a lot of handling going on, there's a lot of lice treatment going on, and there was quite high levels of mortalities that occurred following the consecutive delousing treatments. But what was really notable was that those animals that were fed the much higher level of EPA and DHA had much lower levels of mortality. We're talking about comparing 50% and above when they were at the threshold level to now coming down to less than 20% mortality at the much higher level. So we see that this higher level of EPA and DHA really provides some level of support for animals in terms of managing their stress responses. And there is other studies out there that show that when animals have a lower omega-6 to omega-3 ratio in their diet, that they tend to have a lower stress response in terms of being able to deal with stressful conditions better. So let's look at that immune system. So how that relates in terms of the animal's immune system, and it's obviously primary response to these stressful conditions. We need to be mindful that the immune system in most animals is a multi-layered strategy. The immune system operates principally initially by an external barrier process, by skin and mucosa, trying to limit the contact with pathogens. But then, of course, once the pathogen gets into the animal, we then actually results in a secondary line of system coming into play, that's the cellular barriers. But those cellular barriers too have multiple lines of defense. They have a primary line of defense, the innate immunity, and the secondary line of defense, which is the adaptive immunity or acquired immunity. In that first line of defense, there's basically 2 key cellular responses we see. There's a phagocytic response, which is basically principally about the animal cellular system identifying and exterminating threats. And then there's natural killer response, which is designed to actually elicit more of an assault and removal of those threats. That primary response, particularly the phagocytic response, involves an inflammatory response. So the inflammatory response is a key part of this immune response by the animal, but it needs to be also kept in control. And these different immune responses that we see in the first line of defense and the second line of defense, they actually involve different cells to perform different tasks. Now, where this becomes pertinent to the omega-3 and omega-6 story is that each of these different cells responds to different signals. And those signals in many cases are derived from molecules that are made from the omega-3 and omega-6 fatty acids. So what are these different molecules? Well, in the inflammatory response, the principal molecule that seems to elicit that primary inflammatory response comes from molecules made from arachidonic acid, ARA. These are the 2 series prostaglandins, the 4 series leukotrienes, and the 2 series thromboxanes. So these molecules promote the inflammatory response. And I'll talk in a few slides from now to actually explain that inflammatory response and how it's elicited. But there is a whole series of other molecules which are derived from EPA and DHA, which also play an important role in that inflammatory process. From EPA, there's the 3 series prostaglandins, the 5 series leukotrienes, and the E series resolvins. And from DHA, there's the D series resolvins, the merasins, and the protectins. Now, notably, these molecules that are derived from the omega-3s, EPA and DHA, they have the countering effect to the ARA molecules. These ones have a very low pro-inflammatory potential, or even they have anti-inflammatory or inflammation-resolving potential. In some respects, these EPA-derived molecules are actually the countering signal to the ARA molecules. ARA switches on inflammation, and EPA switches off inflammation. Now, to give you an example of what just one of those molecules does, this is a EPA-derived molecule. This is resolvin E1. And you have to remember that there's dozens of these different molecules that are made from EPA and DHA and arachidonic acid. So this one molecule, you can see it influences about 5 or 6 different types of cells here in terms of the different immune responses by the animal. It can influence neutrophils, it influences natural killer cells, influences macrophages, T cells, and dendritic cells, each with a slightly different response. So you can imagine then what all this full complement, having all these molecules available, is going to do in terms of having that ability to switch on or activate and control all those different cells within the immune system. Now, as I mentioned before, what we often need to look at that is this is in context of how an animal actually manages an inflammatory response or how it regulates an inflammatory response. So let's take an example here, say an animal getting a bite from a sea lice. That sea lice creates a wound, and then bacteria or other pathogens can enter into that wound. That wound, the presence of that wound basically begins the process of the recruitment of platelets from the blood. And these platelets begin clotting the wound to stop the animal bleeding out. It also begins the recruitment of things like mast cells. And these mast cells then also send out secondary factors that mediate vasodilation and vasoconstriction in the near blood vessels to limit bleeding, but also then to start basically signaling the delivery of other cells and also nutrients and plasma into the area to actually start allowing the inflammatory response to proceed, but also start the repair process occurring. One of those cells that comes in from that response is the neutrophils. And those neutrophils then secrete factors that begin to neutralize and kill some of those invading pathogens. But then they also then start phagocytizing some of those pathogens in combination with macrophages doing the same, which also get recruited into the site. And then those macrophages then also secrete other hormones like cytokines, like interferons and interleukins, to then start recruiting other cells to initiate the tissue repair process. Now, that inflammatory response that we get here continues until either the foreign material is eliminated or the wound is repaired. But it also requires that switching off signal to actually allow the animal to basically mediate the initial rush of nutrients and blood into the system to actually allow for the switching off of that inflammatory signal. Now, what's been identified is that inadequate levels of EPA tend to prolong this inflammation process, and that usually occurs as a detriment to the animal. It's having excess rediversion of nutrients and energy going into the inflammatory process if it can't switch it off. Obviously, the first stage of response to an infection or a wound is that pro-inflammation response, and that's about mediating a defense mechanism and a repair mechanism. And this is principally elicited by the ARA-derived eicosanoids like prostaglandin E2, and of course the subsequent cascade effects that occur from that. But we need to turn that inflammation signal off, and that's driven principally by those EPA-derived eicosanoids like PGE3 and also some of those E-series resolvins. So we see that there's already quite a broad range of beneficial effects. We can see that when we maintain this better balance of EPA to ARA in the system to allow the animal to elicit an inflammatory response, but then also bring it back under control. So we can see that there's a range of evidence out there for the way in which these animals can control their immune system and also particularly for anti-inflammatory responses. We can see that by having the presence of EPA, DHA, and ARA in their diet, it allows for improved disease resistance, improved survival when challenged with different bacteria varieties like vibriosis, for example, and also a reduction of bacterial-based mortality. We can also see that it also provides some support in terms of viral challenges as well. But we see a whole myriad of different immune system responses when we have higher levels of these longer chain omega-3 and omega-6 fatty acids in the system. Another one of those, of course, is that primary barrier, the skin response. By having stronger skin layers and improved ability to elicit a barrier function like improved wound healing and things like improved zinc use by the skin cells, all lead to a stronger barrier to actually mount that better primary immune response. But we can also see that having those high levels of EPA and DHA in the diet also links to those better levels of EPA and DHA in the skin. So when we have insufficient essential fatty acids in the diet, we tend to have these lower levels of these molecules present in the skin as well. We've also seen that particularly EPA appears to be quite important for winter wound repair. And again, that's principally about bringing that inflammatory response in wounds under control. Now, this was a recent bit of data. It was actually getting about a decade now, so it's not that recent. But it nicely shows the role that EPA plays in the regulation of inflammation. Now, in this study that was comparing a standard diet against two different functional feeds, this is work done by EWOS, they had two different functional feeds, both with lower fat level, higher protein level, but the principal control point here was about varying that DHA to EPA ratio. So what they've done here is they've dropped the DHA down a little bit, and they've kept the EPA high and elevated. Now, when they fed the animals those diets and then challenged them with Atlantic salmon reovirus, what they noticed is that there was a much lower level of viral load in the heart tissue of the animals that were fed that diet with the lower DHA to EPA ratio, clearly showing that there's a strong role of the EPA in the inflammatory response there in the heart in terms of managing that viral load. When they actually looked at what they call histoscores, which was looking at the inflammatory responses to those challenges, again, they saw a similar response. They saw a much lower histoscore, so seeing much lower levels of inflammation and damage in those animals that were fed the higher levels of EPA. Of course, the other fatty acid, which appears through recent evidence to be having some of an impact in terms of influencing fatty acid nutrition in salmon in particular, is linoleic acid, it's 18,2 omega-6. Now, as we showed earlier, linoleic acid doesn't tend to impact growth much, but it does appear to have quite a marked impact on the animal's physiology and utilization of the other long-chain fatty acids like EPA and ARA in particular. Why this is important to look at is that most of the plant oil alternatives we're using at the moment, like rapeseed oil and camelina oil, for example, are really high in 18,2 omega-6. Now, this data at the top of the figure here on the right shows some work that was done recently by the group at IMR in Norway, where they basically kept the levels of EPA, DHA, and ARA in the diet constant, and then they varied that level of 18,2 omega-6. Now, one of the first things they saw was in the liver polar lipids, these are the structural lipids in the liver, is that as they varied that level of 18,2 omega-6, the arachidonic acid went up correspondingly. At the same time, the EPA came down, and it came down by more than halving its levels. When we look at the graph on the right, further to the right again, what you can sort of see in terms of that response of that 18,2 omega-6 in the diet of the animal on the whole range of different tissues, is you can sort of see that if we look at the muscle tissue, what the animal is fed is pretty much what it deposited in its muscle. But if you look at something like the retina or the erythrocytes or the heart phospholipids, you can see the slope of that line is much less. And what that tells you, the animal's trying to regulate that level of 18,2 omega-6 in those tissues. It's trying to keep it under control, principally because we can see that this is actually having a negative impact on some of the really important functional fatty acids like EPA, for example. Now, when we start learning this sort of data from some of the modern studies, it really pays to go back some of the older studies. And the one at the bottom here is an oldie but a goodie from Gordon Bell's work back in about 30 years ago. When that study, what they did is they just replaced fish oil with sunflower oil straight out. And you can sort of see what they did is that they had a marked impact on the level of the 18,2 omega-6 in the feed and a bit of an impact on the EPA and DHA levels. But one of the key observations from that study of Gordon Bell's was that they had really quite a marked prevalence of cardiac necrosis. This is damage in the heart of the salmon. It was basically almost non-existent in the fish that were fed the fish oil, but those fish that were fed the sunflower oil with the really high level of the 18-2 omega-6 had like 2/3 of all the fish had necrosis in the heart. There was clear evidence that this fatty acid was causing problems. So we can sort of see through, by optimizing the omega-3 levels in diets for salmon, that we can have many different ways in which we can impact fish welfare. There's a clear link between dietary EPA levels and malnutrition and diseases, and by having those elevated levels of these long-chain omega-3, we can improve those responses to malnutrition and diseases. But there is a range of other welfare indicators that have been looked at with respect to nutritional responses. One of those is the internal welfare index, where recent data from the FEMA has shown actually that by increasing the level of EPA and DHA, we can have quite a marked impact on the internal welfare index by getting a much lower internal welfare index, which of course is a positive thing, in those fish fed much higher levels of EPA and DHA. But we can see a range of indicators being influenced, things like group indicators like mortality rates, growth, and disease control can all be improved, as well as individual indicators, things like responses of animals to sea lice, improvements to skin condition, and improvements to smoltification state, and a reduction in vertebral deformities, all occurring with optimal omega-3 levels. So in summary, what I'd like to finish off with is showing you basically a bit of a simple diagram that summarizes a lot of what we've talked about in this presentation. And then we can see that through Optimum Omega Nutrition, we get a range of benefits to fish health and product quality through the application of Optimum Omega Nutrition. We get a reinforced immune system through the use of EPA, DHA, and ARA. We get enhanced pathogen responses in survival of the animals when we have high levels of EPA in particular. We see that there's a role of these fatty acids in the smoltification process, although that changes pre and post transfer depending upon which fatty acids become predominant in that response. We can see that there's greater skin integrity, robustness, and wound healing capacity through the optimum application of these fatty acids, as well as lowering the stress and also improving responses to thermal stress through the application of these fatty acids as well. We can see that there's improved cellular metabolism and energetics, and better bone mineralization that occurs through the use of these fatty acids, and of course, better flesh quality in terms of both pigmentation and melanisation. Thanks for your attention.
Excellent. Thank you, Brett, for a really insightful overview there. Something for everybody, both experts and practitioners alike, I think. So thank you very much for that. And whilst you take a breath, I will remind the audience that you can post your questions in the chat function. Send the questions to staff is the selection you make from the drop-down menu, and then the panelists will attempt to give you some answers. So let's not hesitate and bring the panelists into the discussion now. So if I could invite the panelists to turn on their webcams. We have joining us today from Norway, Kåre Gruven. He is head of feed for Norway Royal Salmon. His background in economy, marine science, and aquaculture was the platform for earlier roles in some big names in aquaculture, EWOS and ACPA in particular. Welcome, Kåre. We have Dr. Neil Ochterlony, who's an independent consultant working with a range of clients in aquaculture, aquafeed, and the wider seafood sector. Very well known to many on the call. Neil was most recently the technical director at IFO. So welcome, Neil. And we have also Ragnhild Blekkenrud, who has a background in biotechnology and molecular biology. Ragnhild has a lot of experience with fish health, reproduction, business development in the salmon industry, both in Norway and in Chile. And she joined Veramaris in the middle of last year to help us with the business development work in the Norwegian market. So welcome to all three of you. And let's start with some questions here to build on that fantastic platform that Brett shared with everybody. And Neil, could I start with you? You've been in this industry a long time. Do you think we really need to prove the benefit of Optimum Omega Nutrition for farmers, or are we not just going back to the way things were done 20 to 30 years ago?
Well, thanks for the question, Ian, and thanks for the opportunity to join the panel today. Brett's covered a huge amount of ground with the science there, and I think that's really important. What we're talking about with EPA and DHA are extremely valuable materials, and their value is both from a nutritional perspective and also an economic perspective. And it's important that we use them to optimal advantage, whether it's production of salmon or whether it's production of other species or indeed for other markets. Now, it's quite clear from the science that Brett's shown that there are impacts on salmon via the physiology and the biochemistry, and that's been pretty well elucidated now. What strikes you actually is there's a lot of quite recent work that was presented. A lot of those papers are 2019, 2020, that sort of thing. So although the science started to develop some time ago, it's really gathering momentum now, and we actually know and understand a lot more than we did even 5 years ago. Now, this is important to have that evidence actually, because ultimately this affects profit margins and profitability and sustainability of the industry overall. And of course, also you want the EPA and DHA to carry over the health benefits to the consumer ultimately as well. So exactly the same biology in the inflammatory, anti-inflammatory response is the same for mammalian systems and human beings. I think we have to understand how we got here, and the background and the context is everything. So historically, if you go back 20 or 30 years for salmon farming development, we're talking obviously about low volumes of production, maybe 10,000 tons, tens of thousands of tons, hundreds of thousands of tons in Norway up until the sort of mid-90s or so. Now, when the volume of production was fairly low, those diets could be made predominantly from fish meal and fish oil, and certainly they're documented as being up to 90% fish meal and fish oil in the early 1990s. Now, that's a very easy and straightforward and good way to meet the nutritional needs of salmon. We know from the biology of wild fish that they eat a lot of the fish species which are actually used for fish meal and fish oil production. So the actual physiological systems are very similar, and wild salmon have evolved over millennia to utilize this nutrition. So you can fairly say that for species like blue whiting, herring, and sand eel, which are found in wild salmon, prey items, that actually they provide pretty close to the nutrition that a salmon would need. Now, clearly, there are constraints on production of fish oil. Fish oil is relatively flat in production annually around the world, and for the last 20 or 25 years, it's been roughly around 1 million tons of supply, of which about 20% is EPA and DHA. We work on a roughly 20% figure. Now, that's not going to change, but we're now dealing with a situation where the global salmon farming industry is in the region of 2.5 million tons production. So it's growing substantially, and certainly there has to be partial replacement of fish meal and fish oil over time to meet the needs of providing that volume of feed. And that certainly happened over that period, and the first real replacement was probably late 1990s with vegetable oil, predominantly rapeseed oil, to replace fish oil when supply was really disrupted by El Nino events. So that was really the start of it. But we need to really sort of understand, and we do know some of the impacts. We know that the omega-6, omega-3 ratio, for instance, has been affected by this, but actually elucidating and identifying the health impacts is another question, because it's been quite complicated to do that. But I think Brett has really covered in a lot of detail actually where we are now with that. We know a lot more, as I say.
Very comprehensive answer. Thanks, Neil. So, you know, it's very clear from Brett's presentation that we need more omega-3, EPA, DHA. The demand is growing from aquaculture, also from animal nutrition, also for human nutrition. The supplements market is growing continuously year on year as well as new science comes to bear there. And we know that the availability of certified sustainable sources of fish oil is limited. It exists and it's limited. So could you talk us through the pros and cons of alternative sources to help us understand that a bit more?
Yeah, we're really talking about 3 different sources overall for EPA and DHA. We've got fish oil supply, we've got the algal oil and algal biomasses, we've also got the genetically modified seed oils. Bottom line is we need more EPA and DHA around the world, so they all make contributions, but they make contributions in probably different ways, and they probably have different contributions to salmon feed in the fullness of time as well. For fish oil, as I've said, there's a long history of production and supporting salmon farming, and indeed you could argue that fish meal and fish oil were the foundations of modern salmon farming because they supplied that nutrition. But roughly about 70% of global annual supply of fish oil is going into aquaculture, of which again about 70% of that volume is going into salmon. So salmon's take is quite a lot. Now there won't be the fish oil supply might be tweaked to a degree, and there are possibilities of other sources like mesopelagic fisheries and zooplankton and such, with the caveat that they have to be adequately managed. But overall, that 1 million tons of fish oil is probably unlikely to change substantially over time. So that's really what we're stuck with. In the meantime, we still have a global salmon industry, which is growing over time as well. The rate of growth might be declining, but it's still growing over time. So we're expecting more growth, certainly in countries like Norway and Chile and Scotland as well. But really, fish oil is kind of stable in terms of what it'll supply. The certification of fish oil is important as well, and relatively high volume of certification to the Murren Trust standard of around about 50% of supply is in place. So that kind of assures that fish oil supply over time, which is important. I would say also that actually, of course, from a nutritional perspective, the EPA and DHA levels in fish oil and the other fatty acids present are relatively close to salmon's needs, as I talked about before. In terms of algal oil, these are relatively new products to the marketplace, and algal biomass, they have a very good fatty acid profile as well. It's very similar to fish oils in a way. They're somewhat like a concentrated fish oil. If you looked at, for instance, the Veramaris product, the combined EPA and DHA levels about 54%, I believe. So average fish oils are 20%, maybe up to 30% in some instances. So they're a bit more concentrated. There's a standard production process in place for producing algal oils as well, which means that supply can be ramped up over time as well, which is an interesting approach. Other fatty acids like arachidonic acid are also present in algal oils too. So nutritionally, we would see algal oils potentially making very important contributions to aqua feeds and feed formulations over time as well, because what they're able to do is actually dampen down the variability that we sometimes see with fish oils, both in terms of supply, but also that concentration of EPA and DHA in fish oils is variable because the fish oils are produced from species which are prone to environmental perturbations and fluctuations and such like, and those wild fish, equally like salmon, are what they eat, and phytoplankton levels change over time as well. So fat levels and EPA and DHA concentrations too. The recent advent of certification for algal products as well was a very interesting development too, and that really supports supply chain and consumer confidence over time. Moving on to the genetically modified seed oils, they're relatively new to the market. Currently, there are 2 rapeseed-based products in the market. There's also camelina oil, which is quite close to commercial realization, but we're really looking at 2 rapeseed products. One actually produces EPA as a source of EPA, the other is a source of DHA. Now, they also have omega-6 and omega-9 present. They do have omega-3, but in the carbon-18 form, the alpha-linolenic acid too. So they're not quite the same substitution from a fish nutrition perspective. And I think that those markets might actually be quite different over time for genetically modified seed oils. And certainly one of the producers of those oils is talking about the nutraceutical market as the way forward for their products as well. And there might be other ways that those products would go into animal feeds too. So they're not necessarily aquaculture, not necessarily salmon, but they're interesting in terms of a global contribution to EPA and DHA. But I think in summary, it's quite clear that EPA and DHA levels in feed are critical, and the science continues to support this, and that's going to develop over time, which is really exciting information as well. I would say overall taking into account nutritional needs, formulation practicality, and last but not least economics. In all likelihood for salmon production, it's going to be kind of a blend of fish oil and algal oils or algal products really that support feed formulators in achieving target EPA and DHA concentration.
Thanks, Neil. I'd like to bring you in, Carrie, at this stage to the conversation, because we've heard a lot about the physiological reasons why we need EPA and DHA in the diet. We've heard about supply and demand from Neil, but you're living this day in, day out. You have animals being held under your conditions. You have a responsibility for the welfare and the health of those animals. So could you help us to understand a little bit about what caused Norway Royal Salmon to reconsider the levels of EPA and DHA in your salmon diets?
Yes, in NRS, we have a high focus on fish health and sustainability. And we always try to optimize the production. And that also means to reduce mortality and get a better fish welfare. So, and for several years, we followed a feed strategy where we use traditional feed types together with functional feeds in specific periods. That could, for example, be before and after delousing during winter, where you have some problems with winter wounds, and also in periods with more handling of the fish and falling temperatures. And we followed this traditional feed regime for several years, but also with minimum effect. Sometimes it seems to be a good strategy, and other times it's very difficult to find evidence that these feed types help us solve these challenges. And there are a lot of different factors affecting the results when you see in the comparing what you see in small research trials compared to what you see in the field. It's very difficult to replicate this. But we know from research trials that EPA and DHA is positive, and it's very positive when it comes to fish health in general. Better pigmentation, dark spots, growth, like Brett presented. When it comes to the functional feeds, it's very difficult to have or find the perfect timing. So with this background, we decided to try to make a more robust fish all the time, not just in a small period of time. And this period where you have these problems, when you face the challenges, it's very difficult to be on time. So more robust fish all the time is probably a better strategy. And hopefully this will give us an effect regarding fish health.
Thanks, Corey.
Yeah.
You'll continue.
Yeah. So when we decided to stop using these functional feeds and then instead increase the levels of EPA DHA, we turned to algae. As mentioned about the levels you have for fish oil, the right way I think is to go for algae and new sources. And also it's a very good and sustainable source.
Okay, and I suspect that one of the factors in your decision making circled around the return on investment or the cost benefit related to changing the nutrition for your fish. So can you talk us through a little bit how did you evaluate that, and how did you for changing your omega nutrition?
Yeah, as mentioned, this is the cost is very, of course, in this time is very important for us. But cost is also fish welfare, less mortality, better growth, etc., better quality. That's positive. So we compare the cost of the traditional feed strategy against this new strategy with adding more EPA and DHA. Functional feeds also have a higher cost. The same with algae, but you can play with these numbers when it comes to mortality, quality, growth, etc. And also you can play with the numbers of inclusion of algae and the percentage of functional feeds. So it's a calculation where you can tune the numbers. And of course, we also look at the end market and hope this could be a more valuable product. But right now, the focus is on the fish welfare. But yes, it's a growing interest for products with higher level of omega-3 and a lower omega-6, omega-3 ratio. But right now, the focus is on fish health and sustainability, less mortality.
Understood. That's really helpful. So, and there's a question from the audience a little bit related to that. How do you sort of manipulate or formulate to optimize the varying requirements for omega nutrition through the life cycle, through the production stages for the fish? You know, bearing in mind that they have different challenges at different stages. So, Brett, maybe you could take that one and just build a little bit on how the farmers, you know, practically utilize Optimum Omega Nutrition, the principles that you presented, in order to tackle the main health challenges that they face in Norway.
Thanks, Ian. Well, there's a range of key health challenges which I guess face the Norwegian industry, sea lice among them, other various inflammatory diseases. But a lot of it comes down to that ability of the animal to mount an immune response and also to control its inflammatory responses. So in a time when, you know, as Neil mentioned before, we'd really decreased that level of long-chain omega-3 in the diets, we were sort of almost handicapping the animal's ability to make a response in some respects. So it's probably almost, you know, not only, it's probably, I think the change needs to be not just formulating to what the animal needs for growth, it's formulating to what it actually needs for functional immune function and inflammatory response management. And what we can sort of see now is that while the threshold level for growth might be that 5% of total fatty acids, I think for probably inflammatory response, it's somewhere upwards of 7, 8, 9 at that level. We're looking at now a substantially higher level. And what that's going to mean in terms of how we manage through the life cycle is that obviously when we're growing salmon in freshwater and the small, the lipid levels in the feeds are a lot lower. We can afford to go substantially higher in the omega-3 levels there. And then when we come to sea, at the very end, we're getting up to almost 40% oil in some of the feeds. We still need to work out a way of how we're going to provide 8 to 9% of our fatty acids as omega-3. And there's obviously constraints in the supply of fish oil there. So things like the Veramaris oil, to me, is a really useful tool to allow us to go down this path to provide some tools to basically help us make animals more robust and more resilient to the changes that conditions we're farming them in.
Thanks, Brett. So Ragnhild, the hour is slipping by extremely fast, but I want to make sure we bring you into this conversation as well, because you're at the coalface in a way, helping the farmers in Norway to navigate this new terrain and to realize the possibilities that they have now with these new technologies that are available to them. So what kind of questions are you fielding from farmers in Norway as they think through the opportunities with Omega Nutrition?
Yeah, well, like Neil was mentioning, the microalgae oil is a relatively new product on the market. So naturally, farmers that are considering to implement this in the feed, they do have a lot of questions about what it is and what it means in terms of benefits and possible cost savings. So typically, the first thing they want to know is the safety of the product and features of algae oil. And questions like, what is the potency? Does it contain GMO? Is it organic? Is it label rouge? Is it certified? For example, these are very common questions to get from the market. And when farmers do understand that this is a registered and certified product and that it's proven to perform, then they start looking at the benefits that it can provide. And this is when I came to realize that they do have an opportunity now to gain back control of the omega levels. So for the past 2 decades, the farmers have had to accept the lower levels of omega. And the reason for this is, of course, that there has been limited resources in the market also from the feed producers. So now they have the opportunity to gain back the control of the omega nutrition, and this is something really amazing. And also at the same time, it's not so strange that it takes some time for them to understand and figure out how they can use this opportunity. So they want to know how much it will cost, for example, and what it means in terms in regards of return of investment. So also they want to make sure that this is something that can improve the productivity, and also that it can ensure the health and the welfare of the animals, and how they can use this to differentiate in the market with a better product. And of course, when the farmers are investing in the algae oil, they want to also know that they can get something back from this investment. And from what we have seen today in Brett's presentation, I think we can clearly understand that there's a possibility of reducing production costs there. So we do know that increased omega levels will increase also growth and reduce mortalities on the production side, and then also create a better product for the consumer on the other side, which is in line with what Kåre was telling us. So that the farmers now have the opportunity to take back control and bring omega levels back to where they used to be, and to do this in a sustainable way that is not interfering with marine biodiversity is really a game changer in the industry.
Understood. Thank you, Ragnhild. I think we're at the top of the hour, but we've got so many questions coming in. I'm going to take one more question, and then we're going to wrap up. I hope if you're able to stay with us for a few more minutes, then you'll benefit from this question, because it's a very common one that we hear, and it's around the relative importance of EPA and DHA, and whether the fish has the capability to seamlessly interchange between the two and produce what they need in order to ensure their health and welfare, or whether we need to ensure the balance of that correctly in the feed. And Brett, I think you addressed it through your presentation, but could you just restate the position on that, please?
Okay, the data here with respect to DHA and EPA and ARH to a lesser extent, if we look at a metric of growth, there's clear evidence that shows we can use just EPA or just DHA or a combination, and the animal is relatively ambivalent in a growth response. But if we move beyond growth as what we're measuring as our criteria for response, we see a whole range of other things occurring. And things like looking at the response to inflammation, the response to, say, disease challenges, changes in the animal's cellular architecture into response to the presence of other challenges, we can see that there's a clear need for both EPA and DHA. And in fact, I guess my views go back to the work that we did in recent years, is that when we give the animal the substrate to make its own stuff, and look what it makes it in a particular ratio, and it leaves it there. It doesn't push it all the way to DHA. It leaves some EPA there as well as DHA there, and a lesser amount of DPA, which is the one in between EPA and DHA. So the animal's telling us. I mean, evolution works for a reason. And I think the fact that we were seeing that ratio of 3:1 to 5:1 for DHA to EPA tells you what the animal wants, really.
Excellent. Thank you very much. Thank you, panelists. I really appreciate your answers to the questions today. And it leaves me now to sum up, I think, with a few short reflections from the conversation we've had here. I think we've heard how farm salmon perform better with Optimum Omega Nutrition, and what that really is depends upon what stage of the production cycle and the conditions in which the animals are being held. And the science tells us, though, that they need more omega nutrition during smoltification, during challenging events in the production cycle, such as disease challenges, environmental stresses, handling events. There are many events through the production cycle where they need more, and especially when they're fed higher lipid diets during the grow-out period. That's what the latest science is telling us, as Brett presented. And exactly how much they need then is becoming clearer, but what we also know is that they need more of certain types of fatty acids at the different stages when they face health challenges, and they need that rapid response from the immune system to counter inflammatory diseases, for example. They need EPA in order to be able to counter that inflammatory response. So with that in mind, Optimum Omega Nutrition, it remains one of the most impactful areas of focus for salmon farmers, and that's why we see so much interest in the area. I think the return on investment is the case for a good return on investment for Optimum Omega Nutrition is quite clear, both from a production perspective, also from a market benefits perspective. And so therefore we're really happy to be able to continue to support the dialogue through this series of webinars and through the involvement of experts that you've seen on the panel here today. So that just leaves me to thank everybody, thank the audience for the questions. Those that we haven't been able to answer today will follow up separately after the webinar. And a special thanks goes to Brett for his very insightful presentation today. Thanks everybody, bye-bye.